Hello, everyone. This lecture is going to be pretty short. It covers sections 12.1 and 12.2. Chapter 12 is about alcohols and phenols. Starting with section 12.1, the structure and property of alcohols and phenols. Alcohols are compounds where an OH group or hydroxyl group is connected to an sp3 hybridized carbon atom. We know that the names of some alcohols already, they should be common to you. Methanol, ethanol, and isopropanol are three common alcohols that you would encounter possibly in your daily lives. Methanol is a compound that can be a byproduct of distillation, and it's actually a reason that you should not drink backwoods distillates. And whereas commercially available ethanol products have to be checked with GCMS, for example, gas chromatography, mass spectroscopy, to check the methanol content to make sure that it's not too high, because this is a compound that is dangerous for blinding you. Ethanol, as a commonly it's in spirits such as wine and in popular in Kentucky is bourbon. Isopropanol is rubbing alcohol. You can also have very complicated alcohols. I've drawn the structure here of cholesterol. Phenols are compounds where the OH group is connected to sp2 hybridized carbon atoms. Remember your hybridization from organic 1, that this atom and every atom in the benzene ring are sp2 hybridized. So this most common phenol is actually called phenol, and we'll discuss naming in just a moment. To the right, we have another complicated molecule called capsaicin, and this is the molecule that's responsible for the hot flavor in chili peppers. This part of the molecule makes it a phenol, but we have other groups that are present in this molecule as well. Here, for example, we've got an ether, and here we have an amide, and finally over here we've got an alkene. So remember those functional groups from organic 1. Nomenclature of alcohols. You want to first identify and name the parent or the backbone of the compound. Then identify and name each substituent that's attached to that backbone. You want to assign a location to each substituent and then assemble the substituents alphabetically. In this molecule, for example, we have a backbone that has 4 carbons in it, so that gives you butane as the parent or backbone. And then we have to make the compound butanol to reflect that the alcohol is in the 1 position. So we've got 1 butanol here, but remember that when we have the number 1, that this is implied. So really we can just call this molecule butanol, and we know that the alcohol is at that 1 position. In the second example, we still have 4 carbons in our backbone, so we're still going to go with a butane as the parent. And then we want to go with butanol to show that it's an alcohol. And this alcohol is in the 1, 2, 3, 4. It's in the second position. So we've got 2 butanol for the name of this compound. Now, you don't always have to call compounds with butanol. with the OL at the end, it's perfectly acceptable to write 2-hydroxybutane, and every organic chemist will understand what you mean. Let's get some more practice with these alcohols. Here we've got a backbone of tertiary butane, or tert butane. And the alcohol is connected at this position, the central position, so we've got tert butanol. In our second example, we still have a tert butyl backbone, but now it's not the main backbone that we should be focused on. We should be focused on this part, which is giving us propanol. So it's propane and then propanol. And the alcohol is at the 1 position, so that is implied. And what we have to add here is our methyl group. So we've got 2-methyl propanol. In our next example, our parent is cyclohexane. So our alcohol is cyclohexanol. We already discussed that the name of the simplest phenol is phenol. You could also call this hydroxybenzene, but no one does. In the second case, we've got a benzene ring with an alcohol, so we know that we've got a phenol, and we've got a chlorine attached to it, so we can call this compound chlorophenol. And we want to number this so that the alcohol gets priority number 1 based on our name, and that chlorine is at the 2 position, so we've got 2-chlorophenol for the name of this compound. And lastly, we've got a phenyl group with a CH2 attached to it. And remember that that substituent is called the benzyl group. So this gives us benzyl alcohol. Physical properties of alcohols. They have a higher melting point and higher boiling point than alkanes and alkyl halides. Here we compare ethane to chloroethane to alcohol, and we go all the way from -69 degrees Celsius to -12 to 78 degrees Celsius for ethanol. Why is that? It's because of hydrogen bonding interactions. That's why we get an increase in melting point and boiling point. And here I've drawn a simple diagram that shows the hydrogen bonding interactions between the lone pairs on oxygen and the hydrogen atoms. And that, of course, is a continuous network that's going to keep going. And raise that boiling point. Alcohols with short chains are water soluble. Ethanol, for example, is actually miscible with water, and that means that any concentration of water will dissolve in ethanol, and any concentration of ethanol will dissolve in water. It's actually really hard to remove water from ethanol to get to a high concentration of ethanol. The highest concentration that you can buy is Everclear, which is 95% ethanol, and you can't get higher than that without doing some fancy things in the lab. When you increase that alkyl chain length, then the solubility of that alcohol in water is it's not surprisingly sparingly soluble in water. Okay, section 12.2 talks about the acidity of alcohols and phenols. You've already covered this content in the chapter on acids and bases, so this should all be a review to you. We know that alcohols are deprotonated, they lose a proton, and then this is called an alkoxide. If you had a phenol that was deprotonated, then this would be a phenoxide. Let's compare the following compounds and their pKa's, different functional groups. We know that alkanes have a pKa of about 45 to 50. Amines have pKa's of about 35 to 40. Alcohols have pKa's that range from 15 to 18. And then our halogen compounds, our HX, range from -10 to +3. How can you deprotonate an alcohol? You need a base whose conjugate acid has a higher pKa than the pKa of the alcohol. And I've written this in a generic equation with a generic alcohol and a generic base. So in this equation, our alcohol is deprotonated by a base to form an alkoxide and our protonated base. So this deprotonated or this protonated base needs to have a pKa of greater than 16 for this equilibrium to lie to the right. Let's look at some examples of where equilibrium lie with different conjugate bases being, the alcohol being treated by different conjugate bases. We can do this by knowing our trends in acidity and basicity qualitatively, and we can also use that table in chapter 3, it's 3.1 I think, that gives us some pKa values for compounds to get us on the right level. We know already that alcohols are more, or have a pKa of around 16. And then on the right side we want to find the conjugate acid, and this is ammonia with a pKa of 38. 38 is larger than 16, so this gives us an equilibrium to the right where we've got a weaker base and a weaker acid. In our next example, we're comparing our alcohol with sulfuric acid, and sulfuric acid has a pKa of -9, and that is smaller than the alcohol, so our equilibrium is going to lie to the left in this example. Then in our final example, we're comparing ethanol and phenoxide, or ethanol and phenol. And you should know without even looking at the table that phenoxide, or that phenol, is going to be more acidic than ethanol because of this sp2 hybridized carbon. These lone pairs can be delocalized. One of them is going to be delocalized into the benzene ring. And you can draw a variety of resonance structures to represent this. This is just one of them. There are 3 more good resonance structures. See if you can, well, I guess let's go ahead and just draw all 3 of them. Right, so those are the 3 good resonance structures, and that tells you that you've got resonance stabilization, and the pKa of phenol is going to be lower than the pKa of ethanol. The pKa of phenol is 10, and the pKa of ethanol, again, 16. So which way is this equilibrium going to lie? It's going to lie to the left. And that's all I have for you today. We'll start with section 12.3 next time. And have a good day.